Hi, I'm Jan-Willem, and I'm on the PageSpeed team at Google in Cambridge, Massachusetts. We work on the PageSpeed optimization library, which includes tools like Mod PageSpeed, Nginx PageSpeed, and Google's PageSpeed service. And today I actually want to talk about sort of a general set of optimization techniques that we've implemented in Mod PageSpeed, but that I want to sort of raise up a level and explain to you how they work so that you can apply them on your sites either with our tools or without our tools. And this actually builds a little bit. How many people in this room went to Steve Souders' talk yesterday afternoon? Great, so I see a lot of hands go up. Steve talked a bit about the importance of getting our site in front of viewers' eyes quickly. And my colleague Ilya Grigorik will be speaking later this afternoon about some of the nuts and bolts of how to make that happen and some of the detailed network performance characteristics that we need to take into account, especially on mobile devices, to make fast web page rendering happen quickly. But one of the techniques Steve mentioned yesterday was trying to get our critical resources up quickly and things like our CSS and images quickly. And in this talk, we're going to be sort of deep diving into specific techniques for doing that for CSS and for images. So to give you an idea of where we want to go, here's the same web page twice. This is for a nearby landmark. This is the ticket page for Radio City Music Hall, just a couple of blocks down the road. And this is a web page test using a simulated mobile browser. And it looks like, you know, from this shot that we're going to have pretty similar page load times for these two original and optimized versions. But when we actually play the video, we discover it's a pretty different experience, right? The optimized page comes in after about 2.9 seconds. The original page takes nearly 6 seconds to render. And this is on a reasonably fast network. When I try it with a slower mobile device, the difference can actually be much more dramatic. And we'll see examples of that later in the talk with some of the sort of stripped down examples, smaller examples that I'll show you. So if there are 3 things I want you to take away from this talk, these are them. One is that the critical CSS, the CSS you need to render your page, you should inline in the head of your document. And you should do that using whatever combination of PHP scripts, CSS compilation tools, or automatic tooling like Mod PageSpeed that you find works for you. Second of all, to get pages to render more quickly on mobile devices, it's useful to inline low-res images that are going to be visible on that first page view. And finally, once you've done those two, we want to lazy load everything else so that it doesn't block the rendering of the stuff that's immediately going to be visible to the visitor to your page. So why are we doing all this? Hopefully this should be preaching to the choir in this crowd, that users expect speed. Now, the 2 numbers I want you to look at on this page, one is actually a little bit hidden away in that top left corner, which is 3 seconds. 57% of online consumers will abandon a site after waiting 3 seconds for a page to load. It turns out most pages take longer than that to load. And probably your pages do. Certainly our pages have in the past and occasionally still do so to our great embarrassment. The other is this sort of perceptual view of user attention, right? That once it takes more than a second for our page to load, our users start mentally context switching. They look away from their screen, they start thinking about something else, and it takes them a moment to context switch back to our website and actually start interacting with our page. So this sort of gives us this aspirational goal that our pages should render in 1,000 milliseconds in 1 second or less. And this aspirational goal, Ilya Grigorik has been talking about this extensively in his past talks, and he'll be talking later today. So you should go to his talk and hear more about how we might make this 1,000 millisecond, how we might break this 1,000 millisecond barrier. The thing I want to focus on here is the big but, right? The big but to reaching this 1,000 millisecond time to glass is that mobile web performance is crippled by network latency. Now, we might hope, okay, mobile devices are getting faster, so in 5 or 10 years, this will be a solved problem. But as various folks have argued in talks here over the years, it's actually network latency rather than network bandwidth that's the problem. And network latency has not been improving as quickly as bandwidth has. And frankly, we need to build fast pages for today's devices. So our problem at the moment is trying to make our site fast today. Yeah, we could wait 5 years and everything will have gotten faster, but by then all our competitors' sites will have gotten faster as well, and maybe the barriers will have moved a bit. So just to give you a sort of vivid example of how much network performance can vary, here we have 2 devices that were sitting in our lab in Cambridge. One is a Razr, a Droid Razr, and one is an iPhone 4. And they're both loading the same Wikipedia page. This is the Wikipedia page for the International Space Station. And there's no optimizations or anything. This is just the Wikipedia page. I visited it last week sometime. And you can see, if I go back, that there's actually a pretty dramatic difference in the load times for these pages. And when you look at the waterfalls for these pages, you quickly discover that all that's going on here is the Razr was running in really bad network conditions. It was getting data at about 1/4 the rate, so unsurprisingly, it took about 4 times as long to render the pages. And if you look, each individual resource is taking about 4 times as long to download in the case of the Razr. And this may have just been because of the position of the device in the lab. It may be because the Razr is an older device and its radio is just not as good as iPhone 4's. The fact is that it's probably a combination of a number of different effects that were all sort of coinciding to make this particular bad result come out the way it did. Now, this I happened to stumble upon merely by happenstance, but this actually happens to us all the time if we're walking around, say, a city like Boston or New York with our mobile device in our hands. Our network performance can actually change very dramatically in a very short amount of time. So given that things can change so dramatically, what I like to do is think about a sort of reasonably pessimistic model of network performance and a very simplified one for sort of my own purposes and sort of understanding whether an optimization on a page is gonna be a benefit or it's likely to hurt me. And so this is a very stripped down version of sort of Ilya's view of an HTTP connection that is hopefully still useful enough to actually draw some conclusions. And so the view here is we've got sort of a 200 millisecond round trip from my mobile device to the to the server and back again, so 100 milliseconds each way. So when I start accessing a web page, what's going to happen? Well, we're going to start out with some control plane stuff where we're starting the radio up. Most mobile web browsers do a pretty good job of firing up the radio before we've actually sort of done pressing the button, entering the URL, and so forth. So hopefully the control plane is not going to intervene too much. We're going to assume we get it for free. Then we have to do a DNS lookup. That's going to take the first 200 milliseconds. We need to establish a TCP connection to the server we're talking to. And then it's only after 600 milliseconds that the first 10 packets of our web requests are going to arrive back at our phone. And that's assuming that the server's been configured to use a 10-packet initial CWIN. So after 600 milliseconds, more than half a second has already gone by, we have 14K of data. And the 14K of data we have is the 14K of data that is at the top of our HTML page, right? We don't have any external resources or anything yet. The next 20 packets after 800 milliseconds, 44K. The next 40 packets after a second. Now, this is actually wrong. These numbers exceed the bandwidth of older 3G networks. So if we're on an old 3G network, we actually won't even get this kind of throughput. It'll take much longer. Now, what happens when we have an external resource like a CSS file referred to from our page? Well, we're going to have to look up our resource domain, and if we keep all our resources on a separate domain, which is what all our web performance optimization books have been telling us to do for years, then we're going to need to do another DNS lookup for that domain name, establish another TCP connection. So by the time the first 10 packets of data arrive for our external CSS file, we've already blown out that 1,000 millisecond limit, right? We're at 1,200 milliseconds just to get the first few bytes of our CSS. Now, we could step back and say, well, all right, so DNS lookup, that has pretty high latency on mobile devices. We could just unshard all of our resources if we're talking to a mobile device. Oh, I should mention, if your site is reached via a mobile redirect, so if people go to your main page and you redirect them to m.yourdomain.com, you're already down there, right? The best they can hope for is waiting 1,000 milliseconds to even start getting your web page. So if we move everything to the same domain, that is our HTML and our resources are on the same domain, we can buy ourselves another 200 milliseconds. And that's potentially very helpful. But as you can see, we're still sort of barely squeaking by, right? We're only getting that first packet of data back for our external CSS file at the 1,000 millisecond mark. And we still haven't had time for the browser to parse it and apply the styles to our page, and that'll take another couple of hundred milliseconds. All right, so that seems pretty bad, right? It seems like we're not going to be able to achieve this aspirational goal of rendering a page in 1,000 milliseconds. But wait, we don't need to render the entire page, right? We only need to render the part that the user is going to see. And that actually can buy us some time to do some of these other more time-consuming tasks, like downloading external resources, while the user is looking at and understanding the content at the top of our page. So the real goal here, and again, this is taken directly from Ilya Grigoryk's talk, is to have one round-trip render for the above-the-fold part of the page, the part everyone's going to see when they first visit your page. Try and do it with no redirects, a fast server response. I didn't even mention server response time on the previous slide. I was assuming your server could respond instantaneously. Everything was in cache, no processing time on your server. And we really need to optimize the critical rendering path. That is, we need to make the browser's job as easy as possible for this above-the-fold content. And so Ilya mentions inlining the critical CSS, removing the blocking JavaScript, and prioritizing the above-the-fold images. Now, removing the blocking JavaScript is an entire talk unto itself, and in some sense, is going to depend heavily on how you've structured the JavaScript on your site. I'll talk a little bit about that at the end of this talk, and we certainly have optimizations in mod PageSpeed that can do it. But it's such a big can of worms that I'm not going to treat it in depth in this talk. So I'm going to talk about inlining critical CSS and prioritizing the above-the-fold images. So there is one other obvious question is, why doesn't the browser just do this for us? Right? Why doesn't if we know that time to glass is a thing that we care about, why doesn't the browser just try and get that above-the-fold portion of the page in front of our eyes as quickly as possible? And part of the answer is that the browser can't actually figure that out until it's already too late. In particular, let's say I have a page with a bunch of CSS files. How does the browser know which CSS is going to affect the styling of the above-the-fold HTML? The answer is it can't tell, so it has to get all of the CSS it can see to make sure that it's applied all of the necessary CSS rules to your page. What HTML is going to be above the fold after styling? Well, I've got to style the page before I really know the answer to that question. How large is each of the above-the-fold images? How much space does the browser need to set aside? Well, I can hint in my HTML about that, and we'll talk about that later. But the browser doesn't know until it has either seen our hints or has downloaded the images and seen how large they are. And finally, is JavaScript going to affect the content of the DOM above the fold on our page? For a lot of pages now, it will, especially if we're using something like image galleries or image scrollers. And in that case, the browser really sort of has no idea what's going on until it's downloaded the JavaScript, started executing the JavaScript. Right? So there are a lot of things the browser just cannot figure out about our pages until it's already too late, until it's already blown away our time thing, our time allocation, our time budget. And so we actually need to sort of hint to the browser to help ourselves along. So step one, prioritizing our critical CSS. So here I have a really simple page, and we'll see the source code for this simple page on the next slide. And on the left, it's unoptimized, and on the right, this keeps doing this to me. I have prioritized the critical CSS. And this is actually running on an iPhone in our lab, and is really not cooperating with me. So what we see is we can actually, for this simple page, which has one image and is mostly just a wall of text, we can actually double the render time of the page simply by prioritizing the critical CSS on the page. And for the page I showed you at the start of the talk, that's actually where we get the lion's share of the speed up. This is by far the more impactful of the two techniques I'm going to talk to you about today. So here's sort of a cut-down version of the source code to that. The thing to notice here is we have a page that has 4 style sheets on it, and those are all external style sheets. And in fact, one of those style sheets has these import statements in it, which if you've read any of the books on web page performance optimization, you know is a big no-no. Import statements, sort of put us even more round trips out before we can get our CSS data and start to render our page. And the other thing is we have this CSS background image. So it turns out the image on that page was actually a CSS background image. It wasn't an image tag. All right. Finally, there's one other thing, which is we've used a really big style sheet on this page. Now, why would you have a big style sheet on your page? Well, it turns out most sites like to use a common site-wide style sheet, right? Do you use all of the styling rules on that style sheet on every single one of your pages? It's very unlikely that you do. And in fact, the statistics we've seen say about 40% of the rules of your CSS rules get used on any given page. All right, so what happens when this page renders in the browser then? Well, unsurprisingly, it doesn't take very long to download the HTML at all. It downloads in 230 milliseconds. The rest of the time is spent downloading all of our style sheets. And we don't actually start rendering the page until 1.9 seconds. And the CSS image doesn't actually appear until 2.1 seconds, which is actually off the side of this graph. So first render at 1.8 seconds. So if we inline the CSS that's actually used on the page, so we just write it out longhand in style blocks at the top of the page, you can see the waterfall looks really very different. Instead of downloading a whole bunch of CSS when we start the page, we're in fact downloading that CSS image. And that's really the only download we're doing, the only external download. And so the first render of the page is happening at 0.7 seconds. And by 0.9 seconds, we have the page fully rendered, including that CSS image. So there's two things that are going on here, right? One is we're able to style the page very quickly. And the second is that we're very quickly able to discover that CSS background image and start downloading it and putting it on the page. Now you'll notice there are some CSS files being downloaded here at the bottom of the page. What's that all about? Well, it turns out there are various options we have if we have sort of large style sheets on our site. The simplest option is we could just inline all of the CSS. Now, I mentioned earlier about 40% of the CSS rules are used on any typical page. But for a lot of sites, it's relatively easy to tweak a PHP script to inline the CSS rather than serve a URL in your page. So it might actually be very easy for you to modify your site and test it under these circumstances and see what happens if you just inline all of your style sheets. But there is a caveat, right? Even after gzip compression, typically a page contains around 44K of compressed CSS. It's quite a bit more than that after you've decompressed it. So that's already going to blow out our first couple of round trips. So that's going to make the top of our page very large if we have a large style sheet and we simply blindly inline it into our page. So test and measure and do what the data tells you for your site. If your site has relatively compact CSS files, this is probably by far the easiest way to achieve this goal. Now, another way, and this was highlighted by Ilya in a previous talk, is to use the Audits tab in something like Chrome Developer Tools, and it'll tell you that you have unused CSS rules and let you drill down into the individual CSS files and see which rules have been used and which rules are not. And then you can use that to identify the critical styles and inline them into your page. Finally, you could use a tool like PageSpeed, like Mod PageSpeed or Nginx PageSpeed, to find the critical CSS automatically on your page. And we have, it's very simple. You just turn on this prioritize critical CSS. Now, the way this actually works is your PageSpeed server doesn't actually know which CSS is critical on the page until it's actually been rendered in a client browser. So what it does is it sends an instrumented page to clients of your site. And your clients send back a list of the critical selectors in your CSS file, and PageSpeed then uses that to decide which CSS to include inline on your page. So there's a downside, right? The first person who visits your page is going to get an instrumented page that doesn't have this optimization applied to it. All the subsequent visitors to your page will get optimized instrumented pages. And we'll periodically re-instrument just to make sure everything's up to date. But roughly speaking, once you've passed that startup, we're going to be able to continuously optimize your page thereafter, even if we're also instrumenting it. The upside is it's based on the behavior of actual clients. So if there are differences in which CSS rules are going to be used for different browsers, right, that's not necessarily going to show up in an audit tab in Chrome if you have, let's say, Firefox or IE-specific or Safari-specific rules in your CSS. So this is actually going to be doing the measurement in individual client browsers, so you should get a good cross-section of all the browsers that are using your content. Now, what's not going to be spotted is rules that are triggered by JavaScript actions. So it may be that 40% of CSS that's used, it's not totally clear exactly what that means, because on a lot of sites, we've included CSS rules that are going to be triggered by JavaScript actions. So if I just blindly look at a page while it's quiescent in your browser, it may be that there's some CSS that's there to perform important styling functions. For example, when I activate a menu, or when some JavaScript code runs on my page. And that's not going to look critical to an audit. And it's not necessarily going to look critical to the automated tools in Mod PageSpeed either. So what do we do about that? Well, one answer is, as I said, if we just inlined all of our CSS then we're done, right? We don't need to worry about that at all. Completely worry-free. Alternatively, we can lazy load the CSS that we didn't load at the start of our page. And as long as we lazy load the relevant CSS before we run the JavaScript, everything should be fine. This is also going to work pretty well for things like printer style sheets, right? We don't need a printer style sheet in order to render our page on the screen, but it turns out browsers will download them when they find them on the page. So how do we lazy load CSS? Well, you could imagine, oh, let's just put a bunch of style sheet links at the bottom of our page. That should be good, right? Well, not really, right? The browser has this look-ahead parser, and it notices the style sheets when it reaches the bottom of the page. And it says, oh my God, there are style sheets on this page that I haven't taken into account yet. I better not re-render the page until I have downloaded all of those style sheets and applied them, because they might change the way the page appears. It can't tell that none of these rules are actually going to apply to this page because you already inlined all of the critical CSS at the top of the page. So instead, we have to be a little more clever. And hopefully the advent of the lazy load tag in HTML will make all of this unnecessary. But for the moment, browsers do not implement the lazy load tag for CSS, and we actually have to lazy load using JavaScript. So what we do in mod page speed is we actually surround all of these style sheets with a no-script block, and then we have a little script, a little fragment of JavaScript, that moves the links out of that no-script block and into a div dynamically after the page is loaded. So the no-script block keeps the browser from downloading the CSS until the script runs. And that keeps the browser from blocking page rendering until it's actually performed the page render, and then we basically uncomment effectively these style sheet links. Question?
Is that more efficient than using JavaScript to actually download it as opposed to the header document?
So this is something we've gone back and forth on, actually. It is not necessarily more efficient, but it appears to be more robust. And in particular, if a user visits the page without JavaScript enabled, this will work. Whereas downloading them by explicitly injecting the tags, we would actually want to inject the tags probably with a script that runs at the bottom of the document or after onload. So this is more robust than doing that. I'm not going to claim that it is necessarily more efficient because it involves a little more DOM manipulation, and DOM manipulation has overhead and costs, and we've certainly seen that in our experiments. So I should say, we believe that you can skip this for non-screen media attributes, and you can just put non-screen. If you have an explicit media attribute like media equals in the link, then we think on most browsers that it should be safe to just include it in line at the bottom of your page. But we are not 100% sure of that. We don't have absolute certain data for all of the browsers that we've tried this on. Okay, so that's lazy loading of CSS and prioritizing your critical CSS. Now, I mentioned the other aspect of getting pages to display quickly is lazy loading below the fold images. And here we're going to get effects like this. So you'll see on the right, we got the page rendered much more quickly, but you'll also notice that the gain was not nearly as large. We didn't see a 2x difference between these pages the way we did with prioritizing the critical CSS. Right? This is a lower return optimization on most pages than prioritizing critical CSS is. By the way, I should mention this is actually on a Razr, so this is a somewhat slower device than the iPhone that we saw earlier. So here's our simple example. So this is a page that actually has 4 different images on it. It has like 5 copies of this icon image at the top that are all above the fold. And then it has a bunch of these other images, one of which is quite large. This puzzle.jpg is quite large below the fold that don't appear on the first render. So how do we make this render quickly? Well, answer number 1 is we could just lazy load all of the images, right? And there are lazy loader packages available. Mod PageSpeed has a lazy loading mode, and I'll show you how to activate that in a few slides. So if we simply lazy load all of the images on the page, that actually works reasonably well. But I should add one caveat here, which is once we start lazy loading images, it becomes really important that the browser know how big the image is going to be after it's loaded. So you'll notice I've added width and height tags to my HTML here. So let's actually take a look. This is what happens if you don't add those width and height tags on the left. You'll see that we actually start pulling in and rendering some below-the-fold images before the above-the-fold image has even been fetched and rendered, because the browser can't tell that it should leave space on the page for those images that occur above the fold. Whereas on the right, we've created image size holes on the page, and then we're filling those holes in incrementally. So without image dimensions, the page is going to reflow on the image load. The other thing is, of course, if there's running text on this page, the text is going to jump around once those above the fold images start arriving, and we really don't want that. So the other thing to notice is, well, if what we care about is performance of the first render of the page, of the above-the-fold content of the page, maybe we just shouldn't be lazy loading the image above the fold at all, right? We should use lazy loading, but we should just use it for the images that are going to be off screen when the user first arrives on our page. Because remember, we're trying to get the browser to fetch the visible page content first. So essentially, we're actually working around that prioritization problem that Steve Souders was alluding to in his talk yesterday, where he said that the browsers would often try and prioritize CSS and scripts over images, because CSS and scripts were going to affect the overall structure of the page, and we're also going to be bottlenecks to rendering the page, whereas images are just going to be bottlenecks to the overall appearance of the page, but they're not going to prevent the browser from actually rendering. So we're effectively telling the browser, actually, these images are important. Start downloading those very quickly. So another variant of the same technique is, rather than just lazy loading the images that are below the fold, we might instead lazy load all of the images, but provide a really bad version, a really low-res version, low-quality version of the images that are above the fold. So I don't know if you can tell from where you are, how many people can tell that there's a difference in quality between these two images? Yeah, I see a few hands go up. When your site first downloads, it's going to take a moment for your users to even notice that that poor quality image is really poor quality. They're only going to notice if it isn't then replaced by this better quality image within a few seconds of the page loading. So what we're going to do is we're actually going to include inline data URLs that contain this very low quality version of our image. And then we're going to replace those lazily with the full quality version of our image. Now, I should mention this technique works very well when we have a number of sort of large images above the fold on our page. And the reason for this, as you can imagine, is because then the data URI that we inline is going to be processed. It's going to actually take some time to process for the browser to process. And in the meantime, the browser is probably also starting to download the lazy loaded image. And we actually can observe that sometimes they race, and actually we never see the low quality version for some of our very small images. We only see the low quality version for the very large images that are going to take a while for the browser to download. So the effect of those optimizations on visual completeness, before we had our page, it took us 6.4 seconds to render the above-the-fold content. After we've added lazy load, it takes 4.7 seconds. Now in this thing, you'll notice there isn't a bar for some of the below-the-fold images. On mobile devices, there's actually one interesting caveat I should have mentioned earlier. When we lazy load our images, it's actually very important on mobile devices that we actually download all of the images at some point during the page render process, either at DOM content loaded or at onload. The reason for that is if we rely on a lazy load solution that downloads our images only when they first appear on the screen, we're going to have a very bad experience on mobile devices. Because it may be the case that in the meantime, the mobile device shuts down the radio and terminates all of the network connections, so that when the user scrolls the page and expects to see those below-the-fold images on the page, suddenly the phone is going to have to restart its network, reconnect, and re-download those images, and that's going to have a very long, noticeable pause on the scroll. So it's actually very important, even though it's going to download more data up front, it's very important to actually get that data downloaded while the radio is warm and live, rather than delaying it until the user scrolls the page. So again, Mod PageSpeed provides this. If you turn on these 3 image filters, it'll lazy load the images, resize the images for mobile devices, and provide that sort of low resolution preview for those images. And in this case, actually, live instrumentation is especially useful because you may think, well, okay, so what images on my page are above the fold anyway? Right? And the answer is, well, it kind of depends on what device is visiting your page. If I'm visiting from a desktop browser, my window could be all kinds of sizes. If I'm visiting from different mobile devices, obviously they're going to have very different screen profiles. So how do we decide which things are above the fold or below the fold? I mean, we can sort of make an aesthetic decision. We can say, yeah, on most devices, these images are very likely to be above the fold. And that's effectively what page speed does. And it does it separately for mobile devices and for desktop devices. Is it serves an instrumented page, and basically the clients are going to vote on which images count as being above or below the fold. And based on the outcome of that voting, we're going to decide that particular images are critical or not. So lazy load your images and use a low-quality inline placeholder for images above the fold. And finally, make sure you load all those images before the radio switches off on mobile devices. So I promised I'd say a couple of words about JavaScript. We're nearly done here. Page reflows due to JavaScript execution are a bit of a problem, and they're a particular problem if what we care about is this sort of 1,000 millisecond time to glass, trying to get a rendered page in front of users' eyeballs as quickly as possible. So one thing that we've observed is that statically sizing areas of your page that are going to then be filled by dynamic content. So for example, if you dynamically load ads, probably we've all had this experience. You go to a website with ads, like a top banner ad, and for whatever reason, the top banner ad takes a while to load. And so we're in the middle of reading the page, and all of a sudden the page jumps about 2 inches down our screen, right? If the site owner had sort of statically sized a region at the top of the page, left a hole there for the ad code to fill in, we wouldn't have had that bad experience, right? We wouldn't have had the experience of our page jumping down the screen. So it's very important when you're using JavaScript to dynamically render parts of your screen that you give some thought to where that content is going to go and what the experience is going to be if it takes the JavaScript a long time to run. Because that's effectively going to be the experience of people on mobile devices. And it's also going to be your experience if you start trying to optimize the performance of your page to get your page to display quickly, right? Is you want to move the execution of your JavaScript down the page and leave places for it to fill in, leave holes for it to fill in. The other thing to do is to consider loading the JavaScript that affects your page earlier. So you may have a lot of scripts on your page. Some of them may be doing stuff that's user visible. Some of them may not. So I would encourage you to think very carefully about what order those scripts get run and where on your page you decide to put those scripts. And of course, if you have asynchronous techniques available to you, then you should absolutely use them. So for example, Google Ads has both a synchronous and an asynchronous version now, and you should, by all means, be using the asynchronous version. So to wrap up, if I have to sort of think about an ideal page load order, what's, in my ideal world, what order should the resources on my page show up? This is sort of my model of the universe. That's that when we download our HTML, immediately after downloading our HTML, we should see our critical CSS, which should be inlined in the page. All of the above-the-fold HTML with the inline image previews should be there. The below-the-fold HTML with image dimensions doesn't need to be there to start that first render, but it should probably be the next thing we care about. And we also need to get the above-the-fold images onto the user's screen as quickly as possible. And then after that, in parallel, we can sort of devote our attention to pulling in the below-the-fold images, the non-critical CSS, things like our print style sheets, and the CSS we're going to need to interact with JavaScript. And finally, we need to download and run all of our JavaScript code. So what this looks like on a real site, I showed you a video at the start of the presentation. I'm going to show you this waterfall at the end of the presentation. You can't really see individual things. What I really want you to focus on here is the colors of these bars, right? On the top, we see that JS and CSS are dominating the initial portion of the load of the page. Whereas on the bottom, we can see we have a little bit of JavaScript code that has to run at the top of the page, but it's really being dominated by pulling in the above-the-fold images, and then we immediately shift our attention back to downloading that JS and CSS. And the result of that is we get this 1.8 or 1.9 second first render of the page versus the 4.4 second first render in the unoptimized case. And then we're able to pull in a low-res version of the page and basically get what looks like a completely rendered page, but with a slightly blurry image at 2.2 seconds. And by 3.7 seconds, we've run enough JavaScript code that we're able to render this dynamic image. So even though we had to run some JavaScript code to get all the images on the page, we're already ahead of the first render that we had on our initial page. So to wrap up, inline the critical CSS in the head of your pages, inline the low-res visible images, lazy load everything else. Thanks very much. And any questions? And by the way, I'll be sitting at table 7 at lunch, so if you want to join us for lunch and chat more. But
so what is the overhead? So page speed transform page transform.
Right. What is the runtime overhead of page speed transforming a page? That varies a lot depending on the horsepower of the machine that's running page speed, obviously. We set deadlines on the order of 10 to 60 milliseconds on the page to try and get things transformed. And what we will do is, if we can't make those deadlines, we'll start serving untransformed content. Now, we do quite a bit of caching. So in the usual case, what should really be happening is we discover already cached, already transformed resources, and we include those in the page and things. And basically, we're streaming content through and adding only sort of an HTML parsing delay, which is on the order of a few tens of milliseconds. Question over there, and then we'll go over there.
This makes a lot of sense for me in terms of the first page view that will land on a site. But I'm imagining a point where you've got, say, 5 or 10K of critical CSS that's making up your navigation and things like that that appear on the top of your page. What do you recommend for subsequent pages? Is there a way that you suggest, like, getting that critical CSS in the cache so you don't have to keep inlining it, or do you just inline it all?
I'm glad you asked that. So he asked basically, this works great for first view. What about repeat view? And what do we do about, do we still need to have all of that critical CSS at the top of the page if we're doing repeat view? I think Steve alluded to, I think in the talk from Microsoft yesterday, we heard a reference to this, which is, you can imagine we set a cookie that says, oh, you already have all of the CSS for this page, so simply refer to the CSS resources unmodified. We don't currently do that in mod PageSpeed, so we'll just keep giving you the inline critical CSS. And one thing I should have mentioned is there was a very small network cost, right, to sending all of that CSS data. That's obviously going to scale up as the amount of critical CSS data scales up. So we're definitely thinking about techniques, and I would encourage you to think about techniques as well. The one we heard about yesterday was, well, let's just set a cookie, and let's assume that if the cookie is set, the CSS is already on the machine in the browser's cache, which might or might not be true, but it's a good enough approximation to work most of the time, we hope. There's a question over here. Oh, okay.
Regarding inlining images, there was a study done by Mobify that I found that data URIs and images on mobile can get 6 times slower than using an external source. So how do you balance that on mobile?
Yeah, so how do we balance the expense of using data URIs on mobile versus using an external source, given that data URIs have been shown to be very slow on mobile? I think part of this is a browser problem that the browsers just haven't emphasized optimizing, but that's the browsers we have to work with, right? Because there's no reason they're inherently slower. We do it by trying to make sure that the data URIs we include on pages are very, very small, right? So when I said we're going to include inline data URIs here, we're talking on the order of like maybe a K of data. for what hopefully will ultimately be a large image that might actually contain many tens or hundreds of K of image data when it's available at full resolution, right? So part of our answer here really is that we're actually trying to move the goalposts and make those data URIs so much smaller than the image that will ultimately replace them that we don't care about the fact that there's this extra overhead. And that, by the way, is one of the reasons why I think it's so important to talk about that optimization is much more effective for larger images, right? Because we want that sort of fairly large difference in size. Any more questions? Thank you very much.